Chapter 3, Section 3.1, Exponential Functions. Let's start with a definition of an exponential function. These functions are denoted by f of x equals b raised to the x power, or y equals b raised to the x power. In this case, b is greater than 0, or positive, and b cannot equal 1, and x is any real number. For exponential functions, the b is the base, and x is the exponent or power. And that's where it gets the name exponential function from. We're going to have a value b raised to the variable x. So instead of x being the base, as we saw in our polynomial functions, it is now the power, hence exponential. Some examples of exponential functions are f of x equals 2 to the x, f of x equals 3 to the x plus 1, f of x equals negative 4 to the x plus 3, and f of x equals 1/2 raised to the x power. These are just a few examples of exponential functions. Notice in each example, the variable x is now part of the exponent. Let's look at evaluating basic exponential expressions using the calculator. We're going to use the caret key, or the power symbol, just below clear. We've used it before to raise a variable to a power. We're going to use it here to raise just constant values to a power. If we look at 5 to the 2.17, we can approximate this using our calculator as 32.87. To its right, we have 3 raised to the negative 3.4. Using the calculator, we approximate that to 0.02. Next, we have 2 raised to the square root of 5. That's approximately 4.71. And next we have e to the 6.1. E is a special base. It's going to be used in some of our applications that we'll see a little bit later. E is approximately 2.71, and it continues. This special base is going to be used when we look at compound interest in terms of investing money, and as well as other applications. On your calculator, your e is located above the ln key. It's one of our second function keys, so we'll press second ln to access the e base. Second ln, and the e should appear, and it should automatically give you the power symbol, or the caret key, and an open parenthesis, waiting on the power on e. Once you get the e and the power key on the screen, you can type in the 6.1 and then press enter, and it should approximate that value to 445.86. Next we have e raised to the negative 0.5. Again, we'll press the second ln. The e should appear on the screen along with the power and a parenthesis. Negative 0.5, close parenthesis, and if we press enter, we get 0.61. If you don't close the parenthesis after the power, it will still evaluate the expression. However, we want to get in the habit of closing that parenthesis for future problems where we're going to absolutely be forced to do so. And last, we have the fraction 1/3 raised to the negative 4. And if we type that into our calculator as 1 divided by 3 and raise that to the negative fourth power, we get 81. So these are just some basic expressions getting us used to the power key as well as the special base e. Now keep in mind that e is not a variable, it is a constant. It doesn't have the same role as pi, but it behaves in some similar ways. Pi is just a constant symbol representing 3.14 approximately. And of course e is just a constant base, in this case representing approximately 2.71. So we'll use the second ln key to access that base of e. Let's look at graphing exponential functions. We've got the function f of x equals 2 raised to the x. I've done a basic t-table of x's ranging from negative 3 to positive 3, and I plugged them into my function to evaluate it. You're more than welcome to use your table feature on the calculator. 2 to the negative 3 is 1/8. 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the first power is 2. 2 to the second power is 4. And 2 cubed is 8. So I've got my input and output values, or my x and y's, which I can plot, and I've done so to the right. I plotted each of the points and then traced out the resulting curve for y equals 2 to the x, or f of x equals 2 to the x. Some special features. Notice, of course, from left to right, the curve is increasing from left to right. The graph has an asymptote, in this case a horizontal asymptote at y equals 0. Notice the left tail of this curve, as x gets smaller and smaller, the curve actually gets closer and closer to the x-axis but never touches it. It gets closer and closer to the x-axis but will never cross the x-axis. So we have a horizontal asymptote at y equals 0. The domain is minus infinity to infinity, and of course the range is 0 to infinity, since we'll never cross through that x-axis. The y values will span from 0 to infinity, and of course with parentheses on all of those. Let's consider the exponential function f of x equals 1/2 raised to the x power. Here we've changed our base. Instead of 2, we're looking at 1/2 as our base. Again, I'm going to use the x values ranging from -1 to 3, and my outputs are 8, 4, 2, 1, 1/2, 1/4, and 1/8. To the right, I've plotted these corresponding pairs and got the resulting figure. Again, you could use your table feature on the calculator as well as your graphing feature to get the same result, but I wanted to sketch these by hand so you could see the resulting graph just by plotting points. If I plot the points and get this picture, we notice that from left to right, this particular curve is decreasing. Notice our last example was increasing, this one's decreasing. We're going to see how each of those represent growth and decay as we move through the next couple of sections. It does have an asymptote, a horizontal asymptote, again at y equals 0. The curve, as x gets larger this time, gets closer and closer to the x-axis but never crosses it. It also has a domain of minus infinity to infinity and a range again of 0 to infinity. So notice the minor differences here between 2 to the x and 1/2 to the x. Let's consider the function f of x equals e to the x. This is that special base e we spoke of earlier. Here I just used the calculator to graph this one. I've shown the table from -3 to 3. These are the resulting values. Again, to the right I have the image that we get from this particular function. It also has a horizontal asymptote at y equals 0. Its domain is also -infinity to infinity, and its range is 0 to infinity. Now notice on the curve, when we graph these on the calculator, it appears as though the left end of that curve actually does touch the x-axis. And that's just simply because of the window we've chosen. If we investigate the table, it never crosses through that x-axis. As x gets smaller and smaller, we get a smaller and smaller value above 0. Okay? So we'll never touch that x-axis, never cross through it, so it's going to be a horizontal asymptote at y equals 0. So be cautious with your calculator windows. It's going to appear as though it finally touches the x-axis, but it actually does not. And again, if you adjust that table and get values between 0 and 1, as x gets smaller and smaller, you'll get y values between 0 and 1 getting closer and closer to 0, but never reaching 0. Transformations of exponential functions. Back in earlier chapters, we talked about transformations of graphs in general. We looked at linear, polynomial, those that were, for example, the cubic function. We looked at the absolute value of x, the square root of x. So we had some basic curves that we looked at. And we talked about their transformations. They reflected, they shifted, and they even compressed or stretched. So let's look at some very basic transformations of exponentials. We have the function f of x equals 3 to the x plus 1 minus 2. The x plus 1, notice that we originally had just x as our power or exponent. Now we have x plus 1. The plus 1 is going to force a shift of left 1, and the minus 2 subtracted from the end of the function is going to be down 2. So the transformation from the basic 3 to the x is going to be a shift left 1 and down 2. So again, if we start with the basic function f of x equals 3 to the x, and transform it to f of x equals 3 to the x plus 1 minus 2, we shift left 1 and down 2. And I've given the image from your calculator there to see that shift. Notice since we shifted down 2 units, we have our horizontal asymptote moved down to y equals negative 2. Our domain is still minus infinity to infinity, but our range changed as well from negative 2 to positive infinity. So we see very similar transformations that we saw with our basic x squared, our basic x cubed, the absolute value of x, the square root of x. This time we just have the function 3 to the x is our basic curve that we're transforming. Let's look at our second example to the right. We have f of x equals negative e to the x minus 3 plus 1. Our basic function, if we take a look at this, is just e to the x. So let's see how it's transformed. The negative out in front means we're going to have a reflection about the x-axis. The minus 3, the x minus 3 in the exponent means we're going to shift right 3. And the plus 1 at the end of this function is going to shift it up 1. Please note that on your slide I have up 2 from the previous example, so make sure you change that in your notes to a shift up 1. So in all, we have a reflection about the x-axis. We shift right 3 and up 1. Since we've shifted up 1, that means our horizontal asymptote has moved to y equals 1. Our domain is still minus infinity to infinity, but our range has now changed from negative infinity up to positive 1. And that's simply because we actually reflected about the x-axis, so it's changed the orientation of our curve. So what's an application of exponential functions? One very common application is something called compound interest, or where we want to look at investing money. The balance A in an account that has a principal or an initial balance of P and an annual interest rate R, which we'll put in decimal form, after T years is given by A equals P times 1 plus R over N raised to the NT. And this is compounded N times per year. So let's back up and look at our formula here. A equals, so our ending balance A, or the amount that we have in the account, is going to equal the initial amount, P, times 1 plus the little r, which is your rate in decimal form, divided by N. N is going to be the number of times it's compounded per year. Now, if it's compounded annually, that's once a year. If it's compounded semi-annually, that's twice a year. Quarterly is 4 times a year, monthly is 12 times a year, and so forth. And I'm going to raise all of that to the NT, the N times T, and of course T is the number of years. In some instances, we may see our investment compounded continuously, meaning that it's compounded at every instant that our money is sitting there. Well, that's going to change our formula since we don't have a value for N compounded continuously. In that case, we're going to use A equals P times E raised to the RT. A is still the ending balance, P is still the initial investment or initial balance, E is that special base E that we talked about earlier, R is the rate in decimal form, and T, of course, is still the number of years. So let's look at some examples of compound interest. Number 1, suppose you invest $25,000 for 10 years at a rate of 5.5% compounded monthly. What is the resulting value or balance in the account? I'm of course going to use the formula A equals P times 1 plus R over N raised to the NT. My initial investment, P, is $25,000. Parenthesis, 1 plus, I need my rate in decimal form, which is 0.055. I'm going to divide that rate by N, which is 12 because it's compounded monthly. That's 12 times a year. And I'm going to raise that to the N times T. N is 12, and T is, of course, the 10 years. If I type that into the calculator, I end up with an ending balance of $43,276.91. Be really careful typing in the power into your calculator. On many of these problems, it's easiest just to go ahead and multiply, like in this example, the 12 times 10 is 120. So you could raise all of that to the 120. Or you could raise it to the 12 times 10, but your 12 times 10 needs to be in parentheses. It must be in parentheses because you want to raise it to that product. You don't want to raise it to the 12 and then multiply by 10. So if you keep it as a product, you need to put parentheses around that power. Or you can go ahead and mentally multiply it out and raise it to that result. Number 2, on the day a child is born, you invest $50,000 into a trust fund at a rate of 7% compounded continuously. How much will be in the trust fund on the child's 35th birthday? In this case, since we see compounded continuously, we know we're using the second formula, sometimes called the PERT formula because of its notation. So we have A equals P times E raised to the RT. My initial investment, P, is $50,000 times E, and I'm going to raise E to RT. The R in this case is 0.07 as a decimal times T, which is 35 years. If I type that into the calculator, I have 50,000. Second ln for E. My power key and my parenthesis should automatically appear. And in the parenthesis, I'm going to have 0.07 times 35 and then close the parenthesis for that product. If I press enter, I get $579,417.34 as the ending balance. The required homework in my math lab at coursecompass.com is section 3.1. The textbook practice is on page 396, problems 1 through 43 odd, and 53 through 56 all.